So as we've mentioned, sets are mutable. However, since they are unordered collection of items, indexing has no meaning. So with lists, seeing as they are sequenced, we can specify an index to bring back an item from the sequenced order. Sets, on the other hand, are unordered, so there is no concept of indexing. So with this in mind, we cannot access or change an element of a set by indexing or slicing. The set data type does not support it. So just to prove this, let's create a very simple set with the integers 1, 2, and 3. If we now try to access the first element in this set, i.e. the number 1, you would think we might be able to put my_set, open square brackets, and pass in index 0. But seeing as they are an unordered collection of items and indexing therefore has no meaning, we get back a type error telling us that the set object is not subscriptable. In other words, we can't use indexing or slicing operations. So with that being said, how can we add an element to a set? Well, if we want to add a single element, we can do this using the add method. So if we put my_set and then utilize dot notation and place our add method afterwards, we can then put the element we want to add inside of the parentheses. So if we put the integer 4 and then take a look at what's stored inside my_set, you can see that 4 has been added to our set. Now the add method is a way of adding a single element, but if we wanted to add multiple elements, we're able to do this by utilizing the update method. Now the update method can take tuples, lists, strings, or other sets as its arguments. But in all cases, any duplicates you include inside of these data structures will be removed. So let's take a look at a couple of examples. If we now try to add the integers 5, 6, and 7 by passing them inside of a list inside of the update method's parentheses, you can see that 5, 6, and 7 have been added to our my_set variable. And it's the elements inside of the list that have been added, not the list itself. Because we know that lists can't actually be included inside of a set, seeing as they are mutable objects. Now if we wanted to, we could pass inside of the update method's parentheses a list, so we could have 8 and 9, and then we could also pass in another set, so we could put 1, 4, and 10. Now if we print out my_set, all of the elements have been included accordingly, however, where there are duplicates, they have not been included. So you can see here 1 and 4 haven't been duplicated, but the number 10 has been included in our set. So to summarize, sets do not have a concept of indexing. To add a single element, we can use the add method, and to add multiple elements, we can use the update method. Okay, so let's quickly take a look at some useful built-in functions that we can use with sets. So if we start with a set called A, which is a set of integers from 1 to 10 in a random order, we can first of all utilize the built-in len function, which we know brings a count of the number of elements contained within the data structure. So if we put len brackets A, we can see that we get back the result 10, which tells us there are 10 elements inside of this set. We can also utilize a built-in function called max, and what this will do is it will find the maximum value within the set. So if we pass in A into the built-in max function, we get 10 returned, but this time it refers to the number 10 as opposed to the count of items. If we use the opposite function, which is min, we can pass A into the parentheses, and this will bring back the value 1 because 1 is the smallest integer within this set. We can also use the built-in sorted method, which we've seen when working with lists, and what this will do is return a new list containing all of the items from the set in ascending order. But we can also turn this into descending order by passing in a second argument, as we've seen previously. So if we run sorted and then put A inside brackets, we get 1 through to 10 in ascending order. Now we can also use the built-in sum method, so if we pass in set A into the parentheses, we get the result 55 returned, which is simply the sum of 1 plus 2 plus 3 all the way through to 10. Now we can also, like we've seen with lists, tuples and dictionaries, perform membership tests. So if we want to check if the integer 1 is in the set that we've stored in variable A, we can put 1 in A, utilising that in operator, and we can see we return the result true because 1 is indeed in the set stored in A. If we put 11 in A, you can see we obtain false as we only go up to 10. Now if we put 11 not in A, because 11 is not in A, it evaluates to true, hence we obtain a true result. So a few built-in functions here that we can use with sets that can come in very useful, and we could also perform membership testing like we've seen with other data structures. Okay, so the last thing we're going to introduce with respect to sets is the concept of a frozen set. Now a frozen set has the same characteristics as a set, so for example, they will only include unique values and the duplicates will be removed, but a frozen set's elements cannot be changed once assigned. So while tuples can be thought of as immutable lists because you can't change a tuple's elements once they've been assigned, frozen sets are essentially immutable sets. In other words, you can't change an element of a frozen set. Now frozen sets can be created using the frozen set function. So let's start by creating a normal set and we'll call the variable A. And we'll set this equal to a call on the built-in set function, and inside parentheses we'll pass a list of integers from 1 to 5. We'll then create a second set labelled B, and we'll have the integers run from 4 to 8. Now I'll copy the exact same code for variables A and B, but this time I'll relabel them to be C and D, and I'll change the built-in function from set to be frozen set. Now if we take a look at the type of variable A, you can see we obtain the type set. And if I take a look at the type of variable C, we get back a type of frozen set. So it's its own class, it's its own object, and therefore they're treated differently. Now with sets being mutable, it means we can't use them as dictionary keys. So for example, if I create a dictionary called my_dict, and I then set this to a set of curly braces, and we have the first key to be the variable A, and we set the value to be a string stating 1 to 5. I can then have a second item with the key B, which refers to our variable called B, and I can then provide as a value with the string 4 to 8. Now when we try to run this, because we're using sets here as keys, and we know sets are mutable, we get back a type error, telling us that we have an unhashable type. However, with frozen sets, because they are immutable, they are therefore hashable and can be used as keys to a dictionary. So if I change the keys in this dictionary which gave us an error to be C and D respectively, when we run this, we no longer get back an error. And I can now utilise the frozen set as a key. So if I was to now run my_dict and place square brackets afterwards, and we try to access the value associated with the key C, which we know is a frozen set, we get back the value 1 to 5. So just by utilising a frozen set means we get some flexibility on the dictionary key labelling. However, we do not get flexibility in changing elements of a frozen set. So if we take a look at the options available to us with respect to methods by accessing the methods on variable A, we can see we have many options, including the one at the top stating add. Now if I take a look at the options available to us on variable C, i.e. the frozen set object, you can see we have far fewer options, and add at the top is not a method we can call because we are unable to add or remove elements from a frozen set. However, we can use frozen sets in the set operations that we've just discussed, so for example union, intersection, difference and symmetric difference. Now, one thing I want to point out here is that if you are using frozen sets in your operations, so for example, if we were to do C pipe D, because both variable C and D are frozen sets, we will end up returning a frozen set object. Now, interestingly, if I start with the variable C and then union variable B, which is the set equivalent of the frozen set, we also return a frozen set object. Now, this is because we've stipulated the frozen set first. So even though we're performing a union between a frozen set and a normal set, we bring back a frozen set. Now, if I switch this around and we try to union variable A, which is the numbers 1 to 5 of a normal set, and we union this with variable D, which is the frozen set with integers 4 to 8, you can see that we bring back a normal set. So we could assign this to a new variable and then utilize the functionality of a mutable object. So depending on whether you include a set as the first item in the set operation, you will obtain the same object type. So make sure you're returning the type that you're expecting to return. So just to summarize, a frozen set is very similar to a normal set, with the difference being they are immutable objects, so you can't add or remove elements to a frozen set. You can use frozen sets as keys in dictionaries because as they are immutable, they are therefore hashable, and you will not run into the type error as you do when you use sets as keys. And finally, frozen sets can be used in the set operations such as union, intersection, difference, and symmetric difference, and if you're using two frozen sets in the operation, you will return a frozen set object. If you use a combination of a set and a frozen set in the set operation, you will obtain an object which is identical to the type of object you place first in the set operation.